Good morning, everyone. So we're going to get started with the next session. My name is Nicolas Papernot. I'm a professor here, an assistant professor here at the University of Toronto, also affiliated with the Vector Institute and the SRI. Today I'm honored to be moderating this session titled Testing Social Cognitive Theory with AI. And so I'll briefly introduce the two presenters, and then I'll let them give a talk for about an hour. And then we'll follow with some Q&A from the audience. So our first speaker is Wil Cunningham, professor of psychology at U of T and a 2023 SRI fellow. His research studies the processes underlying social cognition and emotion, examining how social roles shape one's self-concept and group identity, how cognitive and motivational biases underpin the development and maintenance of stereotypes, and finally, how social pressures help promote prosocial behavior. And then our second speaker will be Joel Leibo, who is the senior staff research scientist at Google DeepMind. His research is concerned with studying cooperation in both humans and machines, and with evaluating AI capabilities. He's interested in reverse engineering human biological and cultural evolution to inform the development of multi-agent AI that is simultaneously human-like and human-compatible. Without further ado, the floor is yours.
Actually going Joel first.
Okay, sounds good. So Joel is first.
All right. Thank you. Thank you for inviting me. And All right. We haven't said anything yet, so I'm not sure why we deserve the applause. But thank you so much for inviting me, and thank you for the introduction and everything. So we're going to talk about testing social cognitive theories with AI. And I'm gonna start with an apology, actually, because all the best talks start with apologies. For people who heard Blaze's talk just earlier, I actually agree with really everything he said. I do think language model-based things are really probably the future of how we're going to do this kind of work. But so far, for the kinds of questions we've been looking at, which involve groups and larger social groups and things, we haven't quite figured out how to do it with language models yet. We're kind of actively doing, actually we are actively doing this together. And so the talk is going to not quite come up to the present in some sense, but we're not really hidebound reactionaries about it. We are moving forward. But anyway, this won't exactly be apparent from the talk. Also, this was a fun talk to put together for me personally, because normally I do all the talking about why we can model social structures and things with multi-agent systems. I've collaborated with Jillian and other people on this kind of thing. But this time we're doing this kind of tag team talk here, and Will's going to do a lot of that. So I'm going to do more of the kind of background leading up to it, and trying to talk about things about how we think about basically deep reinforcement learning in general, and the ideas that kind of are important for anything to do with that, and how it will then flow into the larger social cognitive things, which are things I don't usually get to talk about as much. Is that better? Yeah, cool. Awesome. So let's start. So the themes of the talk here are, so this is, again, about modeling different social cognitive science theories and phenomena and topics and themes using methods of AI, particularly multi-agent reinforcement learning. Kind of another meta theme throughout is that a lot of the controversies are going to hinge on variations of nature versus nurture type questions. So we're going to talk about different ways in which you can think about that. There's a lot of richness of different ways that this plays out in different parts of the space. So I'm going to talk about why, particular models, and then why these kind of innateness questions are relevant to them. Okay, let's go on. Okay, so I said I was going to start early here, and so I went back in time a little. The main point I wanted to make on my 17th century slide was that actually I could have gone back further, right? I could have talked about Plato or something, but I figured, if you're going to go back, you might as well. You have to cut it somewhere. And I actually wanted to say something in particular about Descartes, right? So Descartes was someone who believed that all knowledge comes from basically deductive reasoning. And if you believe that, then you have this problem, which is you need somewhere to start the deduction from. And so that's why he thought there was innate knowledge. And he had he thought the starting point was the thing that was innate, an innate idea. And the counterpoint in the 17th century was Locke's idea some number of years later, where he was trying to refute these ideas that there were innate ideas. And he brought in some interesting elements, which were like patterns of how you might make this kind of argument against an innateness claim. One is to say, well, it's hard to find any statement that like everyone agrees with. So like a non-universality or a diversity kind of argument is one piece of a blank slate claim. Another type of argument you can make is that, well, it's plausible that you could have learned it, right? Maybe it's not. Maybe it was there. People might say, "Oh, you have this idea. It must be there at birth." And then a person comes along and says, "No, it could have been learned very quickly and before you measured it," and that becomes a good argument. Cool. Jumping forward hundreds of years, early in the computer ages, actually, this slide is really the same content that Blaise had earlier, which is that there was really two distinct approaches to thinking both about natural and artificial intelligence. These fields were really linked at that time, and they were a symbolic line of thinking, where the representations were kind of language-like, sentence-like, or logic-like, and the computation was deduction-like, like this follows from that. And then, on the other hand, there was a more connectionist line of thinking, where the basic representations are distributed things, like patterns of activations of neurons, and computation there is more like a flow of electricity in a circuit or something like that. And these these general themes have flowed through 20th century. And meanwhile, in the 20th century, in linguistics departments, there were a fellow named Noam Chomsky was overturning an earlier paradigm, which had been called behaviorism and had been both empiricist and interested in like denying the existence of mental states, though often for maybe more epistemic things. That's kind of a separate point, whether they like fully wanted to say that or not. I think some of them did, some of them didn't. But the interesting thing that matters for us in this talk is that Chomsky then linked the nativism to the symbolic approach. It was so he had this kind of logic-like symbolic ideas, and he connected it to the a claim that things had to be there at birth and not learned. Another thing to say about him that's important is that he introduced this type of argument, which he called a poverty of the stimulus argument, which is really like a theoretical necessity argument. It's saying that this couldn't have been learned. It would have been impossible to learn this kind of thing, so therefore it must be innate. The reason I'm talking about it is we're going to have a talk about computational models of social questions, and people ask us all the time, like, well, how can you ever learn anything about people from a computational from a robot that you made? And you have to understand that the background context is that like people were making necessity claims. Like it was not just that like Chomsky was saying, oh, in humans it happens to be innate. He was saying, no, it has to be innate. Like there's no other way to do it. So therefore, if you can exhibit something that does it another way, it actually does refute it. Another theme that I think we'll come back to. Okay, so. I keep moving multiple slides at a time, interestingly. Okay, so I want to talk for a second about levels of analysis that are useful in neuroscience and cognitive science, other things. So since the 70s, people have been, this is like the first slide of every cognitive science talk, right? You have you want to think about the brain at different kind of levels of understanding it. They're kind of semi-independent of each other. At one level is kind of figuring out a computational problem being solved by say, you want to understand inferotemporal cortex. And you can say, okay, maybe this part of the brain is connected to recognizing objects. And so what would be the kind of computational way in which you would describe the problem of recognizing objects? And then you can talk about, as a separate level of analysis, you can talk about algorithms that might solve that. Like what kinds of things you could implement either on a computer or in a brain that would be step-by-step that would actually recognize objects. And then another semi-independent level of analysis is the hardware under which you would implement the algorithm. Like it could be brain hardware or computer hardware. And this was a super, super influential way of thinking about things in computational neuroscience. The reason I talked about it was I wanted to come to this next, which I think is a point that is a little bit less appreciated. So there's this paper from 2012 by Tommy Poggio, who was my PhD supervisor, and he was one of the authors with David Marr of the original levels analysis anyway. And he asked, where should learning fit into this framework? So there's a couple options. You could just see learning as another computational problem, as at the time he wrote it, I actually thought. But he realized at the time that there was another option as well. You could see learning as something that's kind of above the others. If you identify just a goal of the learning, then you set a goal, like the goal is to live in the world or something. Then through learning, the system will identify the computational problems that it needs to solve. It will develop their algorithms to solve them, and it can even wire up the hardware to implement them. So all of the different levels of analysis can follow from a learning level. And it is sort of semi-independent of the others, just like the levels of analysis framework wanted it to be. So that's how we get to things like you can design a language model without knowing anything about linguistics, where linguistics might be like the computational problem level mixed with algorithm level or something. So we ended up with this kind of picture. At the time he wrote this, I thought it was wrong, because I thought learning was just another computational problem. And he immortalized that fact by, I sent him an email. So he sent me an early version of the paper, and he sent me, and I sent him an email saying, I think this is all wrong. And then he copy-pasted my email and put it in the paper as a footnote, saying Joel thinks this is all wrong. So if you look at the paper, you can see that apparently I thought it was wrong. But now I think it's actually it's obvious that he was right and I was wrong. So okay. So other things that so the point of all that, I keep moving multiple slides. This is I don't know why here. Let's see. Right, deep learning happened. People know that. In around 2012, vision systems started to get better. Reinforcement learning improved dramatically. Lots and lots of other things happened. I could have gone on and on with this slide, and these things were fairly empiricist. I think that was the point I wanted to make here. So most of these models, though they make assumptions, but they tend to be not really related to the domain. Like, it's not to set these things up. They really had the flavor I just was describing, where you set a goal and then let learning figure it out. You didn't. You would make some choices, like how many layers there are in the thing or whatever, but it wouldn't be like, that's not really related to object recognition or whatever, language or anything. It's just kind of like some other thing. I'll say more on that in a minute. But around the same time, and kind of earlier and flowing through, there was another line of thinking that was also around, which was more on the nativist side. So, but this was a bit of a softening of the earlier, so Chomsky's nativist, early Chomsky anyway, he changed his mind over time, but early Chomsky was very, very strict in the things that he thought were innate. It was like really like a logic-based computer program type setup. But these people, like Liz Spelke and Josh Tenenbaum and other types of people, were very interested in a picture of cognition based around Bayes' rule, where in Bayes' rule you have a prior belief distribution as part of it. And they wanted to talk about how you would get knowledge from other knowledge, but with kind of a soft innate idea at the start. And most of these people, well, especially Liz Spelke, thought that there was kind of a limited number of core knowledge things that were meant to be innate. And they're listed on the slide there, like objects, like you should parse the world into objects. There's some way of understanding things in terms of actions, numbers, places, and social partners. And they thought that there would be like a characteristic limit associated with each of these. Like the one that's easiest to remember is the number one, right? Like people usually don't think of numbers as like precise numbers. They tend to think of it as like one, few, and many. And she thinks that was evidence of it being kind of an innate thing because it had this particular characteristic limit that you would maybe otherwise think is a weird thing to have. And so this kind of thing was animating for this sort of Bayesian cognitive science branch. And this was a very, very live possibility, like when I was in grad school and stuff like that. How do I get to another slide? What's going on? It's done something different now. I don't know. What's happening here? Oh, that's there. This is weird how that is completely different from what I'm seeing here. That's the strange thing. I see. I don't know. What is going on? Anyway, people have seen this picture. It's part of the evidence people use for this this kind of stuff. All right. One of these buttons will move to the next slide. I don't know. Yeah, is there a clicker somewhere? Okay. Okay, so I just talked about this Bayesian cognitive science approach. A minute ago, I talked about deep learning. So we have ended up with a question of how do we compare approaches that make different assumptions? And this is a really core idea I put reverse engineering here, but really we could see this as like the way machine learning thinks about the world. The idea is that you have to solve a problem, ultimately. You can have something you can measure and evaluate that you're trying to solve. And then at least locally, you can kind of layer on assumptions as long as you're solving the problem and you're applying best practices to make sure that you're actually measuring generalization. That's the key. Normally, when you're worried about Occam's razor, it's because you're worried about generalization. But if you are explicitly measuring generalization, then you can minimize that worry. Not completely, because there's a million ways that you can do it wrong. You need to apply best practices, which include strict separation of training data and test data, and other kind of making sure that you have multiple tasks in your suite and different a range of things like that people endlessly argue about what exactly is the right thing to do. But if done well, you can minimize the possibility of overfitting. And that's really the core to the kind of machine learning approach here. You can add assumptions like I'll change a convnet, I'll change something that's really like part of the system. Feels like it could have been like for Descartes it would have had to be an assumption at a starting point. But we can change these things and see, well, does it perform better according to some kind of best practices generalization metric? And that's really the core kind of idea that makes this whole type of research possible, really. And there's other secondary things you can look at beyond performance. Like you can look at if the agent learns to solve a problem like humans do, in some look at some secondary behavioral measures, or you can look at like neural measures and things. Okay. Now there's lots and lots of different ways that you might depart from Tabula Rasa, but which is mainly what I want to talk about. But I'm going to start by saying first, the kind of theoretical ideal of being entirely Tabula Rasa, like I will make no assumptions whatsoever, can't work. There are no free lunch theorems. There's also if you assume nothing about the world, then kind of anything can happen and everything could change at any moment, and it's kind of it's a broken thing. There's also many ways to fool yourself, right? You could hide the assumptions from yourself. I like this AI cone that floats around the internet, which I can read aloud, I guess, because it's kind of funny. So it says, in the days when Sussman was a novice, Minsky once came to him and as he sat hacking at the PDP-6. What are you doing? Asked Minsky. I am training a randomly wired neural net to play tic-tac-toe, Sussman replied. Why is the net wired randomly? Asked Minsky. Well, I do not want it to have any preconceptions of how to play, Sussman said. Minsky then shut his eyes. Why do you close your eyes? Sussman asked his teacher. So that the room will be empty. And at that moment, Sussman was enlightened. So there's lots of ways to fool yourself about making assumptions. We do make some assumptions when we make choices about neural networks. But I do think it is reasonable to see these assumptions as sufficiently divorced from the content of what you're doing that it has a really different meaning from, say, making assumptions that really have to do with the topic at hand. Okay, so in some ways, this is really the key slide of the talk, of the first half of the talk here. So there's just many different ways of departing from Tabula Rasa, of adding prior structure and into a learning agent. These all have different interpretations and different things you can do with them, and they're part of the toolkit of doing this kind of modeling. Because ultimately, we're going to talk about social cognitive phenomena modeling. So on the one hand, you can do very explicit, hard-coded logical stuff. On another hand, you could have neural architectures that encourage learning of particular kinds of representations. And then I'm going to keep going and talk about more and more. So, but I realized at this point in the talk, I need to talk first 1 second about how reinforcement learning works before I can really explain the rest. So I'm going to give like the fastest introduction to reinforcement learning possible with Richard Sutton in the audience to tell me if I do it wrong. So, okay, so we have an agent and an environment, and reinforcement learning, people tend to think in terms of the sequence of state, action, reward, kind of on and on forever. Agents send actions to the environment, and environment sends states and rewards back to agents, and we cycle around creating this sequence of things. Another object that is important is a system dynamics function, also called a transition function, which is the probability of a next state given and a reward given a previous state and an action taken by the agent. And this is sort of like the picture of the environment, you can think of it as. And what you aim to do is to optimize a discounted long-term reward called a return. And then another object that's really important is the policy, which is the distribution of actions given state. This is like our model of behavior. This is how we talk about behavior. And then there's a thing called a value function. This is what you're really actually, usually, many times, in different models optimizing, which is like the expected long-term return thing. Okay, so that was just regular reinforcement learning. What's deep reinforcement learning? It's just do all of that stuff with neural networks. Any of those functions I talked about could be approximated by neural networks, and that's really all that one needs to say about it, I think. You can make different things happen by making different choices in how you do those approximations, but fundamentally, it's all just these same objects being approximated in different ways by neural networks. Okay. So now I can explain these different ways that you can depart from tabula rasa in these systems. So one is you can pick different neural architectural choices that encourage learning of different kinds of representations. The example everyone gives is a convolutional neural network is specialized for processing images. It's something where if you think about, you can think about a neuron, neurons arranged over space, like in a retina or in a primary visual cortex or something, and each neuron is looking at a small part of space, like they would call it a receptive field, and multiplying some filter, like those numbers there, by the image. And when you do that, and you put it all back together again, if you assume every neuron has the same filters, you can get pictures that look like that. You could take this input and turn it into that output, which is like an edge-detected version of the same thing. And a convolutional neural network is just the assumption that you're doing the same operation at each point, which turns out to be a really good assumption to make for fission. It makes it much more efficient to learn because what you learn at one point in space can transfer to other places in space. That's the assumption it's making. A recurrent neural network is something vaguely similar, but for time, where you're taking things that learned at one point in time and applying it to other places in time. Many more things you could talk. You could talk about transformers in the same vein. This has become the standard architecture for reinforcement learning agents in my group anyway, where we have images come in, and then we have a convolutional neural network, we have some other layers of feed-forward processing, and then a particular kind of recurrent network, and then a transformation to a value function and a policy. And we do typically actor-critic type algorithms with this. And you can make all kinds of other choices that will help or hinder performance in different tasks. And so one example is this: we had this paper on having agents learn to play capture the flag in 3D worlds. And what helped a lot here was having two different recurrent networks, one that was ticking fast and one that was ticking slower. The slower one ended up being responsible for more like strategic things, like am I attacking right now or am I defending right now, rather than kind of having a superposition of these kinds of things, and it would have some kind of temporal consistency over that. And we do know that this is what they became responsible for because we actually did some kind of neuroscience-like analysis of this network. And then the faster recurrent model, network inside of it ended up being responsible for more kind of quicker term movements and things, temporal consistency of them. And this did a lot better than than this as the standard thing. And that's sort of the way the approach works, right? You know, we have a particular task that we want to do, like beat humans in this game, and that lets us make different things that feel like assumptions in how this thing is going to learn, and we can compare the effect of different assumptions on the output. That's how we do things. Let's see which one works better. Another one that worked out really well. Here, can I play that video somehow? I do want to play this. Is there some, but from. I see. Cool. Okay, so This task is a change detection task in a 3D world. So it's like the agent lives in a 3D world, but then it's taken to the psychology lab in the 3D world where there's a 2D screen again. So you look around, you can move your head and make kind of saccades, or your head and eyes, I guess, are fixed, but you make saccadic head movements and can do program any kind of psychology task. And we did all kinds of stuff with this setup. But this particular one, this change detection task, you can see the way it works is you look to the button on the right if they are the same, and you look to the button on the left if they are different, I believe. And that's what's happening. And you're seeing varied delays between the sample array and then the kind of is it the same array question. And so we found initially most of the algorithms, all of the algorithms everyone was looking at at the time were all failing on this thing, even though it's a kind of a silly, trivial thing. Humans, obviously, you can do it very easily if you just look at this and do it. You probably can't if you're talking, actually, which is interesting in itself. But if you stop talking and try to do it, then it's actually very easy. But we couldn't get any of these things to work for quite a long time. What ended up working in the end. Well, so what was at the time there was a big story about we want to put memory systems into agents that are more sophisticated and stuff. And the problem was basically that agents weren't learning to use the memory system because they were just being trained by reward. We would stick in the fancy memory system, which should make it trivially easy to do this. If it's something, especially something that doesn't need to learn when to remember things, just needs to learn how to recall them. Well, it ought to be able to do this because it's not a hard task. But they weren't learning to use their memory. There wasn't a signal that was coming from nothing about doing this task would get it to figure out I should learn how to use this memory structure that we've put in. And so this ended up being a way to do it. And now I'm trying to introduce a different way of putting assumptions and prior knowledge and things into a system. So this is a self-supervised auxiliary objective, we would call it. And this particular one is called contrastive predictive coding. The way it works is it takes, so we ended up using just a very simple recurrent network for the memory structure in the end for this. And the way it works is it just tries to predict from the recurrent network's state different time lags into the future. The same thing, comparing, is this the same one or not? So it's just comparing time lags, which is a very simple thing to do. But that forces it to remember things and keep them in the recurrent memory, and then be able to have them represented in a way that they can discriminate over time one to another. And once you put that in, then it solves this task. And many other things that required simple kind of memory stuff all kind of became very easy. At least in my group, we ended up putting this in as a standard thing in pretty much everything we did after that. And the point I want to make about this is, there's a sense in which we're changing a loss function here, but we're not changing a reward function for this. The reward is exactly the same as it's always been. The loss function, what's being optimized in by this system, is a sum of the reinforcement learning signal and this other signal, which is about doing this discrimination task on some of the internal signals. And that loss isn't connected to the reward at all. It's just, but it's training the same system, and the overall optimization is sensitive to it, but it doesn't, there's no way to interpret this as doing something that changes the incentives of the agent, which I think has a lot of implications for how we think. When we're thinking about social questions and stuff, we care a lot about when have we changed an incentive or not. And this is the kind of thing that has no effect on incentives, but it has effect on internal representations. And so it's a powerful technique to do this type of thing. Okay, maybe now I can get to the next slide somehow. That's previous. Okay, right. But what if there's multiple ways to solve the problem? We had this principle at DeepMind that we used for a long time, and it became a kind of a slogan for a lot of us, which was what we want to do is search for the minimal set of maximally general priors. So this becomes, again, the Occam's razor-like principle, but it's kind of a meta one that was between projects, right? Within a project, you would have your own kind of way of measuring generalization that would be, that you would use. But then between projects, you would prefer the results of one or the results of another if you thought the priors involved would be more general across different, maybe incomparable things. Another interesting thing that happened before this, around this time, was there was this back and forth with in cognitive science venues with Josh Tenenbaum and Sam Gershman and Brendan Lake and Tomer Ullman and other people. They wrote this interesting BBS paper. I don't know if people have seen this Behavioral Brain Sciences journal. It's a very cool journal where the original authors write a very long opening kind of salvo in a debate, and then they get everyone else to write a response, and then the original authors write a response to the response, and then the entire thing gets published all at once. So it takes forever, but it's very cool in the end. So this finally came out in 2017, but it all happened much earlier than that, really. And they had written this paper that was really back in, I was talking about the Bayesian cognitive science view earlier, where where there was like core knowledge and things. They were thinking about, particularly about like the Atari games that DeepMind had reinforcement learning agents playing, and trying to think about those in a way that was more like, what if you decompose it into objects and make these kind of core knowledge-like assumptions, and then try to derive results from that. So it was something that it wasn't like fully hand-coded because there was learning going on in these systems, but it was something that involved a lot more prior knowledge, structured prior knowledge, than the ways that we had been solving it. And they said that was how the brain works or whatever. And in our reply, we said, well, it's almost like saying that there's a different level of analysis that we're applying here, because what we're doing is saying we're just going to specify some kind of goal and let learning figure out the details. So you say that a concept of objects is super important to solving this problem, and we say, sure, maybe it is, maybe it isn't, but the learning should figure that out. And maybe if after learning, we look at our system and we could do some kind of analysis of what it learned, we could find, oh, there's its concept of object or something. But maybe it won't need that. Maybe the task doesn't require that at all. And that's why this learning level of analysis is really a separate one. And then a few years later, a similar thing happened with another brain and behavioral sciences paper by this guy named David Piotraszewski, I think is how you say it, where he had like a social kind of group cognition version of that, where he had a lot of very particular kind of prior knowledge machinery in his picture. And then we wrote a reply along the exact same lines saying, like, maybe you need that, maybe you don't, and maybe it'll emerge or maybe it won't. And there's a more radical answer to, I think, a similar direction of thinking, which is, I'm putting words in the mouth where the author is now here, but the way I interpret this reward is enough paper, and Richard Sutton's one of the authors, is the hypothesis that maybe it just goes very far. Maybe you need very, very little prior knowledge, like no prior knowledge, and very simple reward signals as well would be enough. And the paper is very radical in the sense that it's not just about like, okay, we're going to put in a memory system and then let the details be wired up. What they were saying, at least the way I read the paper, is that the cognitive abilities themselves could emerge just from optimizing the reward. Like if you need to have a memory or an attention system or something, like that will appear because of the reward. So I think this is also a live possibility within the space. And of course, if you, in the context of different kinds of problems, you'll find different things. So this is the last slide before I switch to Will here. So there's an interesting question of like, where do you draw the line between whenever you're thinking about a cognitive process, you could talk about like whether there's prior knowledge that's, or what, like whatever subsumes, whatever creates this cognitive process. You could talk about whether it's like, big number of like special processing modules or something, or if it's just kind of something that is more ordinary in the sense that it's like subsumed by the same things that other parts of the brain do. This kind of question emerges a lot when you talk about things like faces, where people are like, well, is face recognition like subsumed by something special about faces, or is it just like ordinary vision that happens to be applied to faces? And then there's like versions of this that kind of go deeper and deeper for questions. So there is a part of the brain that responds specifically to faces. There's several parts. And within that, you can ask like, okay, so there is some special region, but maybe it's doing the same kind of computations that other visual areas are doing, but just for faces. It just happens to be localized for that. Or you could say maybe it's doing something really different with faces, like connecting it to social questions in parsing stuff like that. And these are all the kind of the contours of the debate, typically for any social question you might ask. And now I'll turn to Will to ask some, I guess.
Okay. I'll grab my water now. Yes. Okay, so hopefully this will all work. I'm a little terrified watching your going back and oh, nice. Oh, you're right. It's different. Anyway, so transitioning. So I met Joel a couple years ago. I guess it feels like about 2 years ago, year and a half. In this transition with the pandemic and thinking about how I wanted to actually think about social cognition and how I wanted to think about my field of social psychology. And within psychology, my area of interest is social cognition, just putting up a very simple definition of it, right? It's focused on how people process, store, apply information about other people in social situations. And really what the goal is try to think about what the computations are that might facilitate or interfere with social behavior. And in many ways, social cognition, especially in its origins from the 1970s, was a very radical way of thinking about social phenomenon, right? The idea was that we want to ask this question, right? What are the building blocks of social cognition that oftentimes maybe we don't have to postulate terribly many new things? And this was part of the cognitive revolution that was occurring in the late 60s, 1970s. And the idea was simply, well, if we understand the basic mechanisms of perception, memory, attention, attribution, right, we might not need to actually think about anything other than that, other than the social context that these computations or these processes are playing out in. And what this oftentimes assumed was a very kind of domain general, model of mind, right? There's absolutely nothing necessarily special about social per se, right? But really the goal is to think about how the pieces might kind of connect in interesting ways, right? And you get articles like this from one of my PhD advisors, right? The self is a memory system, powerful but ordinary, right? And one of the goals of this paper was simply saying that, we used to posit something called the self, right? The self being its unique set of computational principles. But if we actually just understand the way that memory works, and the fact you have a lot more experience with yourself, all these effects you previously thought required a special self-concept, right, might go away. And of course, in recent years, we can reward maybe all you need, right? Add reward into one of these ideas, right? If we kind of think about the social world as simply reinforcement agents out there trying to make sense of the world, make sense of each other, right? Like maybe this is all we need to understand, right, social psychology. But there's kind of a problem we hit very quickly, even if you simply say reward is all you need. Because what are the rewards? Right, we can start off with some, because you have to code into your algorithm, what are the R's? Right, and perhaps there's some motivation for hedonic pleasure and reward. It's funny, you talk about the loss function as being auxiliary, but maybe there's some motivation for structure and predictability, right? Maybe there's some motivation for cognitive efficiency, right? And the question becomes, how many of these different processes, right, do you need to hard code into the system, right, to give rise to complicated, right, behavior? And this is where social psychology gets kind of murky, maybe, because as you read our journals, there become a lot of them. We suddenly have things like, we may need to hard code in something called the need to belong, right? Maybe as social creatures, we need to monitor how well we're interacting with others. Maybe this is going to be a lot like hunger and thirst, right? I'm going to have an innate module that's ensuring that I'm being accepted by others, and that's going to govern a lot of our behavior. There's a lot of theories, going back to the 1930s and even earlier. Well, maybe a fundamental idea is that we have to maintain self-esteem, right? I need a positive evaluation of myself, and that's going to be a core motive that I have. Maybe there's a power for group-based dominance. Maybe this is one of the reasons why we're so groupy and terrible to each other. Maybe there's a fundamental motivation, right, for my group versus your group. Luckily, some positive ones, right? Maybe we have inequality aversion built in, right? Over time, for various reasons, we decide that we don't like when things are terribly, unequal. And going into the economic side, things like kin selection, right? Maybe for various reasons, I'm going to hardwire. Let's look out for people who might have my genes. And honestly, I could have had the slide go on for days and days and days, and the social psychology field is basically just journals of scales. I guess you get a lot of citations for scales. measuring all these various things. So one of the first questions really is, well, how many of these things do we really need? And then a second question that also comes to the question of origins, right? Suppose by the time you're an undergraduate and you are now in the basement of Sid Smith Hall in a dark room staring at a computer and are trying to figure out how you interact socially, right? You've had, say, 18 years of exposure to the world, right? So you might actually have a need to belong by the time that you've arrived in our lab, right? Was that from some of your individual learning, right? Is there biological evolution? I mean, is it literally, right, hardwired? Right? Or some of these kind of cultural evolution stories that kind of set up the social learning environments and the cultures that we live in. And this becomes very kind of tricky to decompose, especially, as I said, when you typically get our participants 18 years into their life. And even if you study children, right? I have a 5-year-old. I mean, he's basically barely ready to be for a psych study, right? And he's already had 5 years, right, of different exposures, right? And so there's a weird game, right, that we have to play, right? Just like minding your P's and Q's, right? You might need to mind your Q's and R's, right? The idea being in a world where you have kind of reinforcement learning going on, right? What things have you learned, right, to act like a reward, right? And in many ways, that's what a Q is going to be, right? And when I was first getting into this literature, during the pandemic is when I totally radically changed my entire research career, right? I used to read a lot of Joel's papers, and I used to get slightly frustrated because I would always have the same thought. Julie and I have talked about this. I'm like, you hard-coded the answer in, right? And at some level, I wanted things to be really pure, right? I wanted death and reproduction, right? Put that in and let's let everything else fall out. Right? Well, why are you putting inequality and aversion into your models? Why are you doing these various different types of tests? And in many ways, I think that I came to realize that is actually the importance of studying social phenomena in this way, right? And I learned, from meeting Joel that the reason why you didn't oftentimes do that in many of these studies is because it fails miserably, right? And because of that, this sets up a whole new way of thinking about the whole research endeavor that we're doing, right? You can start with the question, how little is necessary for a certain phenomenon to emerge? How well can you do it? And then you start to play the game of, well, what happens if we tweak it? What if we put this reward function in? What if we change the different processes that kind of go into it? And when is the first time that we start observing many of these kind of social phenomenon coming out of our research program? And so in many ways, it's the tweaking of the models that becomes the scientific process that's going in. And I want to be very clear, it's not that it's all going to just be death and reproduction, right? Sometimes you have to add things, but some will be. And that becomes an important part of what we need to explore, right? Because it's obvious some stuff is built in, right? This is children being, born nearly, I forget how old they are with this, but right, your tongue, right, is sensitive towards sweet things. Sweet things are rewarding, right, to a brand new child. Bitter things are less pleasant. So it's not ever that you can have no kind of rewards kind of built in. But again, the question then becomes the game of how few and how do you have to add them. So I'm going to take a domain that, partially because it's a study Joel and I have, but also an area of interest that I have, which is in group formation. Why is it, right, that people form in-groups and out-groups? Why is it that people like their in-groups and a little uneasy, right, towards out-groups? Why is it seemingly so universal? Right? And this is actually one of the fundamental questions in social psychology, for 100 years. And I think one of the best illustrations of studies looking at this is a work by Tajfeld in the late 60s. What they simply did was they presented people with this stimulus. And they simply asked people to estimate, right, the number of dots on the screen. So everybody do that. Okay, if you thought it was above 15, you're an overestimator. Sorry, if you're below 15, you're now an underestimator. I have actually no idea how many are in there. But I should really count this someday, given I have this slide in a lot of my talks. But if you simply do that, and you put people into this really weird group, suddenly you get all these really strange effects. People start giving more money to the people in the same group that they're in. They like them. They're obviously more attractive and more intelligent. And even in studies that we've done using fMRI, right, you even get changes in activation areas like the amygdala and the fusiform face area, right, for your in-group. In our studies, we simply use a 6-word manipulation, right? For the remainder of the study, you remember the tigers, period, right? And we let them know it's completely arbitrary, right? And data like this, I just put it up there. They also like to show paintings. Which painting do you like? Oh, clearly, I know your personality now, right? Has led to all these different types of innate questions. Like, why does this happen? Why is it so universal? Some people have posited, well, maybe there are coalitionary instincts, right? Through evolution and over time, right, people who learned to have their groups versus other groups did better. So therefore, let's hardwire some really terrible racism into you all. Another hypothesis is that, well, you have a fundamental need for self-esteem, right? And you can get self-esteem from your group. So of course, right, if I can get my self-esteem from the groups that we're in, and you're great, right, I can actually get some of that self-esteem. But all of these different models simply are implying some degree of kind of a fundamental, innate aspect of motivation, right, that kind of underlies this. And this is where Joel and I started talking about a year and a half ago, right? And this is where we like this idea. We say this a lot, right? Let's think about the multi-agent reinforcement model as the null model for social cognition. And what I mean by this, or we mean by this, is that it's not that we're about to say is real. Sorry, it's real, but that's a really bad thing to say. It's real. We did not fake any data. But we're not saying this is not the only metric that gives rise to it. But the question is, how far can we push, right, this idea with as few assumptions as possible, right, and still have emergent in-group behavior emerge? Because a great thing about reinforcement agents is they're not born with any coalition instinct. They do not care about their self-esteem as far, well, maybe the large language models do, right? But in general, at least the ones we have, do not care about their self-esteem, right? They are not upset about necessarily being rejected, right, from a party, right? This is as fundamental as we can go with just reinforcement learning, right, and see how far we can get. So here's the study that we ran. It's basically just a coordination game, and what we have are 16 total agents, right? 8 red, 8 blue. And what they have to do is they have to move around this world and they have to collect different objects, right? So I might grab a blue one, a red one, another red one, and say whatever color I didn't say, the blue one. Right, then I go up to Joel and I say, let's interact. And what we do is simply say, what is in Joel's inventory and what's in my inventory? Right? And the more that we actually have the same inventory, the higher the reward that we get. So in that sense, it's coordination, right? Because, right, we need to actually collect things for the interaction, but we also have to select who we want to interact with. Now, to get in-groups and out-groups, what we do is we made 2 different servers, right? One of which, just if you're a blue alien, there's only other blue aliens live on that world. Right, if you're a red alien, only red aliens in that world. And occasionally you get dropped into the mixed server, right? You get to meet all sorts of other people. And what that allows us to do is actually know how much experience you've had with blue aliens, I call them sprites, I call them aliens in my lab, and how much exposure do you have with the red ones. They kind of do this over and over and over. And then we put them in the psychology study. Right? The psychology studies, we pull them out of this world they're learning in. They appear here on, this is over here, on the right. They have to grab these 2 sprites on the left, don't move. And it just has to grab things and go to one of the stationary sprites. And what's nice about this, you can put new sprites they've never seen before. You can put all sorts of different control studies, control experiments in, really kind of getting the idea of, as a single threat binary, right? Who do you, right, interact with? Now, this is where things get challenging, apparently, with the... Oh, and by the way, there's Raphael, who's first author on the paper. OK, let's see. All right, so, yeah, this is basically what they do, kind of learning they're picking up their items, running around, and basically this little beam where they zap each other to actually start an interaction. Okay, go to here. So this is data from a probe early in learning. Oh, yeah, I see what you mean. This is, okay, try this again. Right, and you basically see he's an idiot. He's untrained. Right, so basically just kind of wandering around, doing things and not interacting with anybody. And later in training, right, this little red alien goes and he hangs out with the other red guy. Right, so the question simply becomes overtraining over experience. When you get to this probe task, who do these aliens choose to interact with? And you see plotted on the left this is for a red alien. Basically, over time, they actually do interact much more with the other red ones. It does diminish over time, but I also wonder about 1.5 to the 9 time steps. But at the same time, it takes a long time, right, for this to decrease. And one reason, of course, is that over time, they probably will eventually have exposure with 1.5 to the 9 time steps. But we can also look at the amount of familiarity, right? Because in different conditions, right, there's been more or less exposure to the other group. And plotted, let's see, is there a mouse? Yes. Right, so here's where the 7-to-1 ratio, in-group to out-group, the 6-to-2, the 5-to-3, the 4-to-4. That basically the more exposure you simply have with the groups, right, leads to more preference for the people that you have more time with. So one question you ask is, well, is this simply just perceptual, right? In the sense that, right, the convolutional neural network is just learning things. It has more time to be learning these various, of course it's going to use it. So we have these conditions where what we do is we put a wall in between it, so you can see them, but you can't actually interact with them, right? And so there's something about having the actual interaction, right, with the agents, right, that allows for this effect to occur. Another question you can ask is, well, perhaps these different groups build different strategies, right? Maybe the blue sprites decided that, well, we're just going to grab all blue, right? And the red are going to grab all red. And so maybe they're coordinating, right, on different, elements. So we did a study where we just made just green, right? This is a case, if you think about it, there's absolutely no reason to differentiate it because every alien that you're, or sprite, I'm alternating, you're going to interact with is going to have the same inventory, right? There's going to be no difference in terms of the rewards that you're getting other than the amount of time that you've actually had with it. And again, it's a little bit of a decreased effect, but again, we replicate this effect, right, that there's more of this kind of in-group bias. So another thing we became curious about is what are some of the other implications? Like how might we, sounds bad to say, but make this effect even larger? And one insight that we had about this idea of familiarity, right? When you have more time to be able to kind of interact with someone, you can learn individual differences, right? I know a lot more about the people in my group, right, than I know about strangers. So what we did was we actually gave all the little sprites little individuating pixels. So technically, you can these are not now interchangeable sprites, but rather you can actually learn that that's the Bob, sprite, right, versus say the Sally sprite. And what we did was we actually added information that might be useful to individuate. I always call this the baddie, but what it is that when you interact with these sprites, there's a certain period of time where you freeze to have the interaction go through. Well, what if you froze and that froze was 30 turns, right? So there becomes a cost, right, to interacting more with some sprites over others. And so if you want to maximize your reward, you want to make sure to learn who the person who's going to talk your head off about irrelevant details, right, is to know to avoid them at the cocktail party, right, to be able to get all of the rest of your rewards. And the idea would be, with more exposure, you can more quickly figure out who that is, right, in your in-group. And this is exactly what we find. Just putting the data for what we call the harder condition, the freeze time going from 16 frames to 50 frames. For the in-group, right, there is that effect that you actually are much better at learning who the baddie is, the more bad they are. But you notice it's basically a flat line for the outgroup. That basically there's just not enough time necessarily to learn who that baddie is. And then what you can do is you can now correlate the degree to which the model can successfully individuate who that baddie is and say, well, how much in-group bias is there in the task where they actually are doing selections between, say, strangers or other types of aliens, other types of sprites. And what we're finding is that degree to which there's ambiguity, right, in who that baddie is going to actually lead to more avoiding, right, of that outgroup. So in that sense, that there's a learning mechanism of individuation coming from familiarity, right, that actually can drive these kind of in-group behaviors. And what we think is really important about this is that this is one of those times where we didn't actually have to postulate any other type of motivation. Right? There didn't have to be power dominance. There didn't have to be self-esteem motivations. There didn't have to be an innate sense of groupness. But a simple, very simple RL, in this sense, could actually explain some aspects of social behavior. And from this is a great time to actually talk a little bit about times where this isn't the case. And I realize all those studies were Joel, so I am going to give time to Joel.
Let's see. So in that study, nothing was needed, and we've had a range of different things, or basically different things end up being needed for different studies. And exactly as Will said, the methodology has usually been we would prefer things that don't assume anything, but we kind of add assumptions until things work, typically. And so I'm about to tell a story where we did need to do something. And so this environment, which is called Commons Harvest, it was inspired by thinking about studies of tragedy of the commons and things, and reading a lot of work from Elinor Ostrom, and a particular paper from Marco Jansen and Elinor Ostrom. But anyway, so here's the picture, the way this works. So agents move around in a 2D world like that. They get rewarded when they eat an apple, and they, as in all of many of these things, including the one Will talked about, they have a partial viewing window around themselves. They can't see everything; they just see a little, what's in front of them. And then here's what makes it a common pool resource, where you can kind of worry about sustainability, which is what this is trying to be. So the growth rule for the apples is density dependent. That's the key idea. So if there's a lot of apples bunched up together, they'll grow very quickly. But if there's very few apples, or if a patch is depleted, they will. If a patch is depleted, they won't grow at all. But if there's very few apples, they'll grow very slowly. So so that means that there are kind of sustainable and unsustainable ways of eating. If you kind of eat all of the apples in a local patch, then you've destroyed that patch. But if you kind of eat some in the patch and then move on somewhere else, then they'll grow back by the time you come back. And then there's some other things to say here, so episodes last a certain amount of time and then it resets. So this is modeling like a renewable resource. It's not modeling some kind of like peak oil type thing where it's like once it's gone forever. This is some kind of resource that regrows every year, and you get to redo the whole interaction each year or something. And also, agents have the ability to zap each other, so we can study sanctioning and things. The zap is a timeout, so if you get hit by it, you get removed from the game for a little while. That's all it does. But there's no inherent motivation to do that necessarily. It's not connected to the main reward of the environment. So if you make this a single-player game, then it's stupid easy for reinforcement learning. This is more or less the optimal thing to do in this map. Just kind of don't let either of those patches get depleted and run back and forth, and any reinforcement learning algorithm at all will discover this very quickly as a single agent problem. But if you now can click to the next slide. Oh, I've gone too far. Yeah, so this is what it's a multiplayer thing. So it just, I usually play this video several times because it's like if you blink, then you miss it because it's so fast. So it's a multi-agent thing. Whoops, I lost it. It becomes very difficult because there's this kind of everyone wants to eat the apples before everyone else eats them, and so there's no way that they could ever discover that they can leave them behind. So in the single agent case, the reason it worked and was easy was that they would, in some early episodes, they would deplete all of the apples, and then they would get a low reward, and they would learn, oh, that's a bad thing to do, and can keep going. But in the multiplayer case, they never get that credit assignment. The credit assignment is impossible because if one agent shows restraint and just doesn't eat the last apple in a patch, then some other agent will eat it. In fact, the other agent is even more incentivized to eat it because it can get, I can get one more apple. So there's no way to discover the fact that all of the gradients here are pushing them toward eating faster and faster. And that's why this becomes so fast, and they just instantly eat everything. So it's a very hard problem, and it's one where learning makes things worse, actually, because if you at the start of learning, when everyone is random, they actually do okay, and here learning makes them do worse. So how can you solve this? And what the way we ended up solving it was we needed to make some change to, in this case, to an actual motivation. But I think it has subtle interpretations that I want to try to get across here. So the thing that we did and was to take this model from a paper by Fair and Schmidt from 1999, where they had this advantageous inequity aversion term. You can sort of see this as like a kind of a funny model of envy or something like that, but maybe it's, if envy is a weird word, just forget that word. We call it advantageous inequity aversion. What it's measuring is deviations from, like the deviations from the average reward where the others are higher. So we're saying that this agent is going to get a penalty when other agents are doing better than it is doing. That's the way to see it. Okay? It's not deviations to the average, it's deviations to the self. That's what it is, actually. It's like we're if you look at the equation there, we're measuring each deviation from every other to ourselves, and then we're only looking at the ones where the other agent got a higher score than I did, and then we're summing those up. And that aggregated thing, that becomes a penalty on the real reward. So it's like we just get a little bit less reward whenever others are doing better than us. That's why envy is a reasonable word. And when you do this, what happens is that remember the zapping beam again. So some agents learn to use the zapping beam to zap the agents that were eating too much too quickly, and because that alleviates their envy, right? Alleviates their advantageous inequity aversion. That penalty term goes down towards zero because they're zapping the other player, then they get less reward. But also, the player that got zapped, from their perspective, now eating too much too quickly is no longer rewarding. It's a policing effect. So they learn to not eat too much. And that ends up working. And this is a way to restore this and make it so that they can learn to just all run around and not deplete the apples. So this is a solution. I think that's the last slide here. Oh yeah, I'll talk about that in a second. There's more things we can say about what it means here. So the way we think about these intrinsic motivation terms is it's very important that they are negative and that coefficient outside of it, the alpha here, is very small number. So all of these penalties are tiny compared to the real rewards in the game. Like, the way to see it is it's more of like an equilibrium selection effect. Like, there are different ways that this agents can go about things here. There's like a really bad Nash equilibrium where they are all eating nothing because they've depleted everything. And then there are other equilibria where they are policing each other and all happy. And this, in these small differences in the reward function, which are like less than a tenth of the actual reward of eating an apple, can nudge it toward a different attractor in the space, a different equilibrium. And I think that's really different from the picture you'd get where if you think about, normally when you think about like I put in an other regarding preference as an intrinsic motivation, you think of it as like a really strong motivation that's like really comparable to the other things. But here, this is small and it's only negative, in fact, so that it can never actually positively get them to do anything. All it can do is they can alleviate this a little bit it's like they could solve the problem in multiple ways, and they can, out of those ways, they might as well select the one that alleviates the small penalty. Most of the early learning has to be about the main part of the reward, which is only from eating apples. And this is really secondarily something that happens. I think that's really important for the interpretation of how this works. Another thing that's interesting about this, about the particulars of this, is there's a kind of aligning in making temporal credit assignment easier interpretation of this particular thing that we did. if you really wanted to learn from the tragedy of the commons, the depletion of everything, that's pretty long-term credit assignment between like, okay, I ate too many apples now and then a lot later, then all of the apples are gone. That's hard to learn from. But this puts the policing action much closer. So you get you suddenly eat too many apples right now, and then the agents that are going to become the police feel this pang of envy, and then are much more quickly, they're right then motivated to go and zap you, and they learn to do that, which then causes you to learn to not overeat. So it's kind of a making credit assignment easier thing. Since then, we found a million other ways of solving this problem by putting in different kinds of intrinsic motivations and things. We never really found anything that didn't require anything, but we have a long sequence of different things that have done, some from us and some from other groups as well. Like Dylan Hedfield-Manel has a paper also solving this in another way. But it turned out to be an interesting problem because it was like you had to add. It seemed like we needed to add something, and then there were many choices for what kinds of things could be added. And I'll probably leave it there and go back to Will.
Thanks. So one of my favorite definitions of social cognition, and I had no idea who said it, is social cognition is cognition where the stimulus looks back. Right? And the reason why I like this is that there's a sense in which the things that you're doing actually affect the minds of the people around you that change their policies, which then has to change your policy. Not only that, the things that you do in the world can actually change what the world actually is and even the things that you're learning. And one thing that really occurred to me as I started kind of getting into this domain is that most psychology studies look like this. Right? It's the participant in the sub-basement at U of T, in a dark room, staring at a computer. And no matter what you do to that face, it's not going to get outraged, it's not going to go, it's going to reappear, you get to meet it again. And I guess I will give who said this. It was one of the comments in graduate school that one of my mentors at the time, Liz Phelps, said that I was so frustrated by as a first-year graduate student, right? We were talking about what social cognition was, what cognition, and I was trying to be very profound, poorly. And she said, well, you know, social cognition is just cognitive psychology with faces. And that was just like the gut punch of the day, right? It's like, if you think about what you're trying to do, right, you're saying there's memory, there's attention. What you're basically saying is that there's no difference between what you're doing and a fractal, right? If you get this with a fractal, you get it with people. How interesting, right, is that? And at some level, as I've aged, I've started realizing her critique may have been more and more and more accurate because, you know, a chair does not mind if you misgender it. A person might, right? And it's a very, very different type of interaction, and starting to have the realization that social cognition needs to be multi-agent, right? And how do we actually go about studying things that have these properties, right? And this really goes that social behavior is by definition multi-agent, despite the fact we have a whole science of single agent, right, social cognition. And so we want to try to ask the question, like, well, can we take our social cognition research and try to explain what looks like much more large-scale social behavior, right? Where the agents themselves are changing the environment by the beliefs, attitudes, and expectations that exist, right? What I believe changes, say, the way Jillian acts given my expectations. I can potentially bring about things given my beliefs about the world. And so this is actually one of the very first studies we ran with actually as of a month ago, my lab is now the Social AI Lab, so we've rebranded, the first of the Social AI Lab. And we really want to look at this idea of behavioral confirmation within one of these multi-agent settings, right? And behavioral confirmation, right, is an old idea in social psychology, right? And the idea simply is that, right, we think about stereotyping, you're in the environment, you're learning about the environment, you're learning statistical regularities, right? And so in that sense, the stereotype, right, is out there, right, to be learned. But what if actually having the stereotype itself causes the regularity in the environment that is the learning signal? So here's the task we came up. It's a little bit modified off of the AI economist paradigm. And we have different agents, and they can chop wood, right? They can mine stone, they can build houses, they can sell wood, they can water stone, they can buy water stone. And you basically get coin by building houses or by selling resources, presumably to someone who would like to, build a house. So how do we get some of these kind of stereotypic kind of expectations, right, into this environment? Well, what we basically do is we color code our little aliens, or our little robots, right? So there can be little red aliens, there can be little green ones, there can be little blue ones. And what we can do is we can actually vary kind of like how good, right, on average, say red aliens are, say, chopping wood, right? How good are they at building houses, right? And we give them just actual skills, like attributes, right, that interact with the environment. And what these attributes really are just it's like a dice roll in D&D, right? Where basically, if you're good at chopping wood, well, 80% of the time you try to do that, it just succeeds. If you're terrible about it, it might only be 20%. So now we have a situation where imagine we have a red alien. Red aliens, on average, are good at chopping wood, but we can also have these poor, red aliens that are really good at mining stone. Well, this is where we put another little trick in. There's actually a market where you have to go sell things. So basically, the way the market works, right, let's suppose, I think of the audience, Sendri, right, comes to me and says she has wood to sell. Right, I'm going to guess what she has. And if I guess wood, the transaction goes through, right? We've coordinated our responses. It's fantastic. But if she shows up with wood, and I'm like, thank goodness you brought that stone, the transaction fails. So now there's a weird social task here, which is that you know what you're kind of good at, but you have to be guessing what I'm going to be guessing that you're going to be bringing, right, for this task to occur. And in this situation, if I have the wrong belief about you, you actually might be doing a suboptimal policy because you need to actually do the thing that you expect me to give you. So the first thing we want to do is simply test the standard social cognition hypothesis, that it's hard to actually deal with large populations, right? There's this idea that maybe we were evolved with 150 people, right? So let's scale up a model where it actually deals with a small population, right? A larger, a larger, a larger, a larger, and simply see, well, how long, if you're just having an observer model, guessing what everybody does, how long does it take for this neural network, right, to learn? And so as you go from a population of 30 to 100 to 300 to 600, as you expect, it takes a lot longer for the neural network to learn it. But the important thing is the neural network we set up for this prediction can solve this task, right? And so the model has the capacity to be able to individuate, right, everybody. Okay, so what if we now do it where, right, we have the color-coded information, right? So basically, on the left, we removed all the color. Everyone just has their individual kind of pixel information, right, that tells you, right, who everybody is. I'm going to put the confound in. And what you find is that, again, on small populations, they learn it fairly well. But as the population size increases, they start actually treating the minority agents, right, that look like the majority agents and guessing wood, right? And the idea simply is it's learning a generality, right, on top of the individual kind of information over time. So I'm going to kind of walk through this slowly because it's a very complicated figure. What you can see here on the left is now on the top, it's how much do agents say mine wood? No, chop wood, and mine stone. And the bottom is how often do they say sell wood, or try to sell wood, or try to sell stone? And we find is that, well, everyone starts off trying to do the thing they're good at. But over time, the minority agents actually start to do the thing that they're actually less good at, right? And they have to spend a lot more labor to actually get the resource to be able to sell. On top of it, if you look at the experience at the market, that means the market actually sees a lot more of the majority agents. So first of all, they're there a lot more often, and when the minority agents appear, they're usually not bringing the thing that they're actually good at, right, but rather the thing that's expected. And what's really important about this, if you think about what's going on here in terms of a positive feedback cycle, the expectations and a little bit of a correlation in the environment is actually creating a more regular environment that's now being used as a learning signal for the other agents to be learning, right? The expectation itself is creating, right, that feedback cycle. So this is where we decided to get really kind of funky with this, right? Let's start off with them learning a small group, right? We know the model can do that. We know it can learn the individuals quite well. But let's say every so many epochs, 20% of the population, right, gets removed with new agents that are all identical. All new agents after that very first interaction, right, have exactly the same skill set. Well, that means by a certain point of the study, there's absolutely no difference whatsoever, right, between any of these aliens. And what if we get really crazy, which is later on, we also get rid of all the market people, right? So let's clear that memory as well, right? And by the end of the study, we have all new agents and an all new market, right, learning about agents that actually all have exactly the same skill set, right? And so on the top panel, right, you see the learning over time, right? They do learn to individuate the majority and the minority agents, but with replacement, it goes on and on and on to the point where by the end, ironically at the end, this is where everyone's at the same, right? And you have the people who are not good at chopping wood. But critically, this is the important piece, because the idea is the stereotype itself is creating the regularity that's being learned. We can say, who went to the market with what? And it's not that this market is being irrational. The actual learning signal of the market is becoming more stereotypic, despite the fact that the stereotype is actually gone from the population. What we're doing now, actually Eric's here, did some of this coding, is doing a behavioral version of this, right, where you can actually go in and you can play against the neural networks, right, either right, as a player or in the market. And what's really important about this is helping ask that question. You know, why is it that there's bias, despite the fact we don't want there to be bias? And we have a whole line of work with my former graduate students, Thalia, where one of the things that happens is everyone thinks their priors are correct, right? It's very easy for people to see stereotypes in other people, right? Because people think that their expectations, their beliefs are accurate. And so those are beliefs, not stereotypes. Given this is actually the stereotype causing the learning signal, what we predict to find is the participants will do exactly this behavior, and it will not be correlated with any prejudice scale. It will not be correlated with any of your values, because, again, people have the experience not realizing they themselves are causing the regularities, right? They don't see their own biases kind of going into it. And I see we're kind of running a little bit out of time, but I just want to kind of do the last bit of this a little bit quickly. My origin, like a lot of us who are kind of playing in this domain right now, has an origin in cognitive neuroscience or computational cognitive neuroscience. And I now am excited about going back to this. It's something that I haven't done, right, for some time. And I want to go back to when I was a graduate student about like what I was obsessed with. At the time, there were so many different theories about things like implicit bias, automatic prejudice, right, and all these different theories, right, about why it was the case that you could say self-report one belief, but maybe self-report another. And Dan Gilbert had this amazing chapter in his dual process book where he gave the example of a soda machine, right? All you know is you take a cup, you put the cup in, and Coca-Cola comes out. How'd that happen? Well, there could be two tubes, right? One tube has the seltzer water, right? And one tube, right, has the cola, right? And it mixes. It could be it's giving you root beer until it inhibits root beer, right, and gives you, the Coca-Cola that's already mixed. You might have 6 different tanks, right, and he kind of goes through all of this and says that with all our behavioral studies, right, it's really difficult to actually know which of those hypotheses gives rise to the behavior, which is why we have 17 different cognitive models, right, of exactly the same, phenomenon. And at the time, this is where I thought the brain was going to be fantastic, right? I'll go do some MRI, we'll figure out which theory is right, and that was just a giant black hole. My career. But I think this is now time that I think with these multi-agent neural networks and the level that we can kind of specify neuroscience could be kind of exciting again, right? Joel alluded to this idea that a lot of social cognitive neuroscience work, right, especially in the late 90s, early 2000s, we're really asking this question, what's built in computationally? Right? This isn't about the rewards anymore. Right? This is to say you actually need a separate face region. Right? You need to have a separate theory of mind region. And oftentimes this was shown simply by saying that in this task versus this other task, this brain area lit up. But there was very rarely a computational account, right, of why that was the case. Again, we're getting better at that. Right, and so going to this idea of what's necessary, right? Does social cognition require specialized hardware? But I think the better question now is what are the computations that would be necessary, and how can we tie those computations, right, into the models and the predictions we're making? Right, and so for the first part of this talk, we kind of started with this, right? We're going to play the game of social cognition by saying, at some level, reward is all you need, maybe some different memory systems, right, and ask the question, like, how do you build these loss functions, right, to be able to understand social cognition? But there is another variant of this, right, which is building very, very different types of neural architectures, right, ones that model, say, a hippocampus here on the right, although I'm getting more and more convinced I should just put a transformer in. But again, naively puts, whether it's a transformer or a hippocampus, something that kind of has this idea of pattern separation, pattern completion, right, to build kind of episodic memories, right? What if we think about gating of active maintenance, right, of different kind of goal systems, hierarchical predictive coding, right, in terms of the fact the brain has many more connections back, right, than forward. I think it's always interesting that these deep neural networks are very forward models, but the brain and the way we act are very backward models, right? And maybe this is a time now with the tools that we now have in the computation, right, to, in addition to changing the rewards, build different brains. Right, because this is where I'm still an optimist. I know that everything gets really excited with AGI, but I still think that people are, at least for now, better at social cognition than neural networks. We're a little better at fast mapping. Whenever we do models, there's always people get excited and they say, well, you know it collapses after 1 million trials. What doesn't collapse? My 5-year-old son. Right, there are things still out there that I think that we can kind of learn, right, from people. And there are hypotheses about things like theory of mind. There are computational models that we can actually start putting into code to see what kind of predictions they make. And as Joel said, go back into looking at what the humans do. And do the humans do things that look like we're like one model than the other model? Right? Are the errors, right? We oftentimes think about AI as being succeeding at a task. Looking at how the model fails at a task, right? And does the model fail in the way that humans fail? Right, and this is actually a slide I stole from Joel. Just all the different levels of analysis that we can start building up. I would normally go through this, but we're running out of time because I really just kind of want to get to what I think is a research agenda for a new way of thinking about kind of social cognition. Again, this is a paper that Joel and I are working on, right? Which really is that thinking about new research goals and new benchmarks and kind of building a new kind of computational social cognition. And there's a lot of questions that have to be asked. Right. The first question is, what are we trying to understand? Are we trying to understand AIs? That is an entirely different set of questions than understanding humans, and they're both valid. Right? We have human-computer interaction. We have computer-computer interaction for things like theory of mind. And in that sense, coming up with a model that does theory of mind even better than people, right, is a totally valid research agenda. But that's a different one than if you're trying to understand what humans do. Because then it gets to the question of what's close enough, right? Because all models are abstractions. How many simplifying assumptions did you make, and were they kind of acceptable? You're never going to do a one-to-one model, right, of the brain. Right? These agent-based models have been used for decades, right? And Joel never says it, but I believe his work shows that these are better versions of this, right? And we've always had these mathematical models of human behavior, right? We're now in a situation with things like Joel, we talked to him later about his melting pot competitions, right? We have these different environments where different agents can kind of play and say who wins. But I was thinking we could even have different types of melting pot competitions where you say which models look more like humans as opposed to which ones kind of do the best behavior in terms of all of our kind of theory testing. Right, and the last thing I want to say is that one thing I think where social psychology has always been a lot of promise and not as much substance are our discussion sections. We love our 5-millisecond effects with our effect sizes of about 0.01 and immediately talking about how Congress needs to change everything about the way that we do everything about education, right? And if you push us, we had a great explanation, and I'd still buy it, right? A 5-millisecond effect in the basement where I've controlled everything, including the fact there's no light, and I still got this effect. Imagine what light would be like if it scaled, right? But it's always this imagine how it would be, right, if it scaled, right? We say things like, well, imagine the nonlinear dynamics of this playing out over time. Feedback cycles, the compounding effects of all these together, right? And again, I still believe that, but I think in these kind of multi-agent environments, we can actually test the discussion sections of the things we've been saying for 50 years. And the last thing I want to say is that we talk a lot about interventions in our discussions. Interventions are tricky. They can be unethical. They might fail. You don't know what the rebound effects are. This is a great place if you want to, Joel was talking about doing interventions on some of the stereotyping work, right? You can actually do interventions in an artificial environment to look at some of the negative potential consequences before even doing an intervention, right? And this is a way that social psychology, if we're modeling this properly, can allow us for a whole new way of doing things. And with that, thank you.
All right, thank you so much, Will and Joel, for this really inspiring talk. I'm going to open it now to questions from the audience. So does anybody want to go first?
This is just, okay, yeah. Super cool. Obviously, as somebody who's interested in these things, I love all of the questions that you're asking. I guess in thinking about the work that you've done, right, to instantiate these questions about innate versus learned, and how many different little mechanisms do you need? I wanted to hear you talk a little bit about not the mechanisms of the agent, but the environment that you've designed that the agent has to learn about, right? So, why is it that the thing that determines a transaction is similarity of goods in one case or correctly predicting what the agent has in another? How much does that determine the results you're getting? Why is that the right assumption for how these interactions occur? I assume you're basing this off of some reasoning about how the world works, but that to me, it sort of ends up being it's not innate in the agent, but maybe it's sort of innate one step back in the environment that produces this behavior.
About that study,
Yeah, I'll do
and then
that.
I'll do my
Perfect. It's kind of we share thoughts.
Yeah.
I think that's a great question. And honestly, I think what you try to do is come with an environment that as close as possible approximates what you think is going on. But that's no different than any other psychology study, right, where you come up with some abstraction that you think represents it. I think one powerful thing about this is that you should probably be using multiple different environments. And a very powerful thing about doing this is that you can see if it replicates across different domains. You can easily change the environments, and all those environments become parameters. Right? Take, for example, the study that we were doing, where every time we got an effect, we worried about a confound. So, let's make all the gems, right, green. Could this just be the fact that the convolutional neural network is having more exposure, right? Okay, let's make it so that they can see. And I think what's really powerful about this, and I think it's even slightly more powerful, is well, I don't want to say it's easy. I guess when we're collaborating, it's easy with computing. That what you can do is kind of just run many more simulations and try to actually have as many environments as possible. And then that becomes like a random effect, right? It becomes when do you see it and then when don't you see it. And in that sense, when you're doing this, it's not just like when you're testing, say, a DQN versus actual critic model on the Atari suite, right? In which one wins. Both the agent and the environment, right, are the independent variables of the study. But again, just like any psychology study, you do your best guess to approximate as much as you think, and that's a great job for reviewer B to tell you why it's not the case.
I'll give a version as well, kind of broadly about this type of modeling. So for me, one of the basically actually the most influential thing on my thinking was reading Elinor Ostrom's work about tragedy of the commons and sustainability and different institutions that work in different resources, right? Different kinds of natural resources give rise to different kinds of social dilemmas and call for different kinds of governance strategies. That's really the kind of central insight from a large part of her work. It's like different resources are different from each other and demand different solutions. And she's done many things. That's one thing that I took a lot from. And for me, that was like hugely inspirational. And what we've been trying to do is create suites of environments, like large numbers of environments, as many as we can, that model different resources. That particular one was a particular had a particular common pool resource type structure where there were certain timescales of things happening, certain ways the agents could interact. But we also have many others where some are more like, say, public goods or something like that, where you're like building something rather than like the worry is about overconsumption. Like they're just very different. These are different settings from each other. You can have models of like irrigation systems and models of forests and models of fisheries, and they're all different because they have different properties. There's different ways to sanction, different ways to monitor, and what we want to do is have a large suite of different environments, what we have, where you can measure the same. You can have each algorithm tested across all of them and see the pattern of results. That's what Melting Pot is. So Melting Pot is this open source thing that we put out with a whole bunch of different environments. Now we're running a contest at NeurIPS for people to submit their agents and have them run them across all these environments. Each task is like they kind of have to come up with a little governance strategy within the little world that they're in to solve these kinds of like the tragedy of the commons type picture I showed before. So that's really how I tend to think about it, right? You don't want to. We are interested in the particulars of the individual environments, and we do expect them to be different from each other, and that is actually meaningful. And we have theoretical things we can think about for why that variation exists and what does it all mean.
Hi, thanks very much for the talk. And I wanted just to pick up on this, the tragedy of the commons idea. The one proposed solution was the policing algorithm, which you could change the weights of. The setup also reminded me of the conformity experiments that are so classic in psychology. And I wonder if one way to change the environment in a larger way would be to look at bringing a social factor in, so the social becomes the environmental factor. So what if you had a seed of one nonconformist who didn't immediately rush off to eat the apples? Could that be enough to cause a pause in the system that would allow the others to discover the more sustainable solution? So the social action becomes part of the environmental variable that feeds back into the whole system, if that makes sense.
I guess the question is, how could we construct a model where that would work? I mean, if you just did that with nothing, right? Like with a totally vanilla reinforcement learning agent that is somehow, like a self-interested rational thing, if you just say, okay, force one of the 12 agents to just stand back and not eat anything, that one agent will just get a low reward and the others will ignore it. But if we could, the way we tend to think about it is like, well, if we want to have an effect where that works, what kind of cognitive process or architectural thing or intrinsic motivation or auxiliary objective or something could be put into them such that they might care about that? And maybe you could make something that make them think like, hey, why is that other one standing back? Maybe there's some good reason, and they might have to, you could imagine something that could work based on that data. But I don't. It wouldn't be clear exactly what it would be. Like maybe there'd be many ways you could do it.
Social acceptance.
maybe one way is like you could have like a social norm kind of bandwagon effect type model, and then you have like a trendsetter, like a norm entrepreneur who sets who does, that. I think I'm really interested in social norms and that kind of model in general, and I think this sort of sounds like the setup of a trendsetter type experiment. I think that could work.
So, great talks both, and really nicely interwoven. And I made a lot of notes as you were discussing. I've had a bit of a fight with Josh Tannenbaum, maybe unsurprisingly, about sort of those different views. And one of the things that occurred to me in your talk is that a lot of these disagreements, I mean, everybody agrees that learning rules everything. The question is at what time scale? Like what's happening in evolutionary learning that then ends up hardwired in the next stage. So there's sort of a ladder of meta learning that scales from nothing but molecules that are reproducing each other to societies with a couple of stages in between with multicellularity and then wiring of brains and so on. So I guess my question is, have you tried to think about what the unifying meta learning rule really is, or observation, that would allow for the whole ladder of different kinds of rewards to emerge, in that sort of multiplicity of scales, as opposed to freezing things at the point where evolution has already happened and we're just defining a brain architecture or a reward architecture that's sufficient for some particular social phenomenon to arise. Because it seems to me like there's something deeper that we're sort of missing.
Should I take that?
You go
I have
first.
two answers in mind, actually. I'll give the answer that I would have given over the last bunch of years, and then I'll give a new answer. So the thing that I have been saying in response to this kind of question for a while has been, it's sort of ambiguous. What are we modeling in terms of the timescale, right? Like people often like to think of reinforcement learning as like a lifetime or something like that, and then maybe an episode is a year or whatever you want. But what seems more natural for this stuff, especially when I'm thinking about the kind of stuff Elinor Ostrom talks about, and these kind of communities where they've kind of negotiated a governance strategy or something, it feels like it's reasonable to think about like a community moving over time. So something in the like time scale of like a cultural evolution type time scale, but maybe relative, not crazily long, like not back to Homo erectus or something, but more like the timescale of people who live in a place are partially by trial and error figuring out how to govern their fishery. Like that sort of timescale is the way I would interpret things. And so you can think about the different motivations and things that when we build things in. It's like, well, maybe some social norm for fairness emerged or something, and that's what's going on in this inequity aversion experiments or something. That's how I've been thinking about it for a long time. I think now we have new opportunities since we can do similar kinds of things with language models, and they might have different interpretations now. And what's really interesting there, well, a bunch of things are interesting. One is there's a separation between the pre-training, which that might be evolution, and then there's what you're doing at test time, which is going to be in context type stuff. And that's an interesting aspect of it. But another thing is like, what are the environments? I still think we need to have some kind of simulated environment where language models will take actions in by saying, I will do this. And once you do it that way, then we have a bit more freedom on the timescales of the environments. So these reinforcement learning environments, the way we think about them is they tick step after step after step, and there's a fixed time stack, a fixed clock in reinforcement learning. But there's no reason we have to still do that when we have a language-first environment. It could be that time step 1 is year 1, and then time step 2 is year 1,000, and we can have just totally arbitrary jumps in time. Or it could be could even be like dependent on what happened. Like we just they make some choice, and then we choose to simulate a little more down the line. Like they decided to plant these crops, and then next thing we'll simulate is when they harvest them, and then the next thing we'll simulate is when they have a meeting about who sent too many animals to pasture or whatever. Like we can just kind of zoom in on the interesting spots without having to have like a fixed clock anymore. So I think there's going to be just so many new affordances as we figure out how to take this research program into using these new methods. And
Just super quick response to that. The apples also engineered the people.
Mm-hmm.
So, this is also social. I mean, there's a social psychology element there as well, I think, that is not.
Yeah.
So many thanks to both of you for the talks. I found them very interesting. Something I'm really curious about with your research program is sort of the extent to which it can accommodate the plasticity of the human reward function, right? Whether it's not just that, I mean, it seems like you have various possible types of human reward that your simulations can model. You can have agents that have a greater or lower degree of inequity aversion or more prosocial motivation for certain kinds of distributions. But it doesn't seem like what we reward itself turns into a potential target for learning in your models. So the agents are just seeking better means in their current social and environmental conditions to satisfy some very rigid set of prescribed rewards that they have. And it seems like there's a contrast there with human social learning, that when we send each other evaluative signals, such as praise and blame, those are not treated by agents as environmental rewards. We don't treat other agents just as particularly complex and potentially difficult or frustrating parts of the environment. We treat other agents as potential sources of insight into what is to be valued, like what we should be finding reward in, and that's something that really sort of sets our species apart from other types of animals that can only punish each other with pain and pleasure. We can send each other sort of communicative signals about what's worthy of pursuit. And I'm just kind of curious whether the kind of learning we have from each other in social environments can be modeled within the work that you're doing, or if that's just going to be automatically sort of an ill-founded question. Like, it seems to me one thing we could be trying to do socially is to come up with objective functions that are jointly satisfiable in the social environmental conditions that we find ourselves in, so that the maxims of our action could be universalizable. And
I
I'm
love
just
this
curious
question.
whether you
I've
can
got
model
so
that.
many answers I want to give as we're. I guess that I have layers of answers, right? So one thing is we have evolved reward functions many times in these kinds of experiments. There's in the capture the flag work I mentioned. In that case, the reward function actually was completely kind of learned from like which reward function is the best. It was like an evolution algorithm running outside of the inner loop of the reward function. Of the reward learning. We also did that in a cooperation type environment like the tragedy of the commons one, actually the same one I think, where there was evolution outside of a outer loop of evolution around a learning loop, and there the big question was, would we get something that looks like this inequity aversion rule to evolve around the learning? And what we found is exactly what every evolutionary biologist would expect to happen, is that if you just use a completely self-interested fitness and do nothing else, then you don't evolve a reward function that will lead to altruism. But if you do something that ended up looking a bit like group selection, then you can evolve the ones that do look like this inequity aversion rule and have other regarding preferences. So that did work out pretty much as people would expect. But I think there's a deeper question here, which is like more about like less about how evolution can tune reward functions and more about like how people in their actual lives and in a faster time scale can kind of negotiate and come up with better reward functions. And we have one model which has a little bit of that flavor. And so what we were thinking about was modeling social norms. This is a line of work that has been with Jillian, by the way. And at least in one version of this, agents are paying attention to what other agents are sanctioning, and then they represent that as a norm, like the things that are sanctioned are the things that are transgressing the norm. And then you can kind of see it as like, well, they're seeing what the norm is, and they'll learn to not transgress, right? So this is a case where it's a bit bandwagon effect like this particular model, but they're kind of negotiating together what is a good norm for this environment, because it's dependent on what's actually working for them.
And then you have to freeze the norms, so there's no ongoing learning, because when everyone's
it does freeze,
obeying
it breaks
the law,
if you don't, yeah.
when everyone's obeying, they no longer get the kind of signal that they need for ongoing reinforcement learning.
Yeah,
Which
that
might be
one
a problem.
has to be frozen at some point.
Yeah,
Thank you.
I agree. It's a great question. In my lab, we spend a lot of time thinking about trying to make things I always say, like, let's have reality try to be as much the grounding principle for what we're doing. And what I mean by that is that oftentimes that I was thinking about like maximizing Atari games, right? And if that was like what a reinforcement learning agent would do, like your goal is like at your deathbed on like 30 million in Pac-Man, right? And that's kind of not the way that like humans, you know, interact. And that's why I really want to start thinking about, you know, this maybe for some people, you know, this death and reproduction, right? In a sense, and you know, not experiencing pain. Right, and for me, I'm curious about how few primitives you need to have to actually get the fact that, you know, if you are making a look of displeasure at me, right, I have learned that actually leads to, you might be voting me off the island, and if you vote me off the island, that's really bad, right? And so the way we've been approaching it is trying to see whether we can have all those things become learned not as ours, but as cues in terms of the things that are predictive of what you really care about.
Secondary reinforcement
exactly.
kind of
Yeah.
picture. Yeah. We have a question from Rich.
Tara.
Oh, okay. Hi, my name is Prajna, and I thought this talk was really fascinating. I think a question, if you haven't already discussed something along those lines, is what if the agent or multi-agent sees nothing productive at all, or if it fails to detect the benefits of this bandwagon effect that you speak of, or if it fails to see the reward or already senses satisfactory conditions already existing. What are the implications of this? Is this something you've explored? Curious to know your thoughts. Thank you.
So,
Why don't you?
well, I mean, what's actually kind of interesting in looking at this is, you know, we're talking about the mean level, right? There's a lot of individual differences when you're modeling, say, in the study that Rebecca and Yukai ran, right? Yeah, we had 1,000, you know, agents, right, in that environment. And it's interesting that not all agents, for example, I'll get to your question in a second, but not all minority agents actually did the counterproductive, like the market actually did individuate some of them, right? And so therefore, right, they actually went along with, you know, what they were good at. And again, we also get neural networks that just like just blow up for, you know, various reasons. I think that when that happens, you probably want to look to see whether you can learn anything about what happened to the experiences of the agent, right, that led to non-learning. Because sometimes, like, you learn more from the failure, right, or the participants, you know, the outliers that didn't do what was expected, right, than you did from what you know was expected. So if I had an agent that learned nothing in my environment and other ones did, right, that might be a great opportunity to learn about what was the experience of that agent, right, in that environment.
Thank you.
Oh, so here we are, the absolutely interdisciplinary conference, and we're hearing some very interdisciplinary talks like yours. And that's really cool. I love that. I love interdisciplinary work. But of course, you know, one way which it can fall down is when we work between the disciplines and we end up without any discipline. And one useful thing that the disciplines do is they give us measures of success. And so, like, we may work in between some disciplines, but I think every once in a while we have to turn and say which measure of success are we contributing to. So I want to give you guys a chance to comment both on how this aspect of of interdisciplinary work can be challenging, and then to clarify, you know, which one of the disciplines do you consider yourself, you know, primarily to be contributing to? So let me just give one example to make that a little bit clear. When you simulate the tragedy of the commons, you know, in some sense, you set it up. You already had the idea of a tragedy of commons, and you reproduced the phenomenon. And so, what is that a contribution to?
Yeah, I mean, I can. So the way we I guess, we write different papers. Some papers have computer science contributions, some papers have social science contributions. But particularly for the social science ones, like the strategy of the commons stuff we were talking about, the thing I showed you, yeah, that's an effect that was known, and we reproduced it. But we have lots of other examples where we try to show something, where we find something new. And there are lots of affordances with this kind of model that you don't have with, say, that the competing model would be like a model things as prisoner's dilemma or something like that, which is, there's a giant industry of people modeling with iterated prisoner's dilemma, and you can get similar kinds of effects. You can show a tragedy of the commons and all this kind of stuff. But what you can't do with iterated prisoner's dilemma is like, what if there's a wall in the middle and everyone has to walk around it? That just becomes like, I don't know, I'll change the numbers in the matrix or something. It's not a satisfying way of doing it. But what we can do with models that are kind of more spatially embedded like this is we can get at the ways in which, like I was saying earlier, like how in Elinor Ostrom's work, there's a difference between a forest and a fishery and a pasture and an irrigation system. Like we can embed those differences in a way that kind of makes sense. Like an irrigation system has like a spatial orientation to it, and that makes sense in this kind of modeling language. In Prisoner's Dilemma, all those things I just mentioned, every one of them, they're just prisoner's dilemmas. I mean, you just like you can't you get stuck because there's no systematic way to put in the difference between a forest and a fishery if you're just gonna abstract it down to the level of the payoffs in a prisoner's dilemma looking matrix. But here you actually can, and so when we're thinking of it that way, we do see effects that are sometimes interesting to social scientists. A lot of the time, we find things that are the same as what social scientists already thought. But I think that's good. That's validating of the research program and gives us more confidence for the cases when we do find something new, like in a paper with Jillian is, I think, one of the best examples. But
Yeah, it's funny you asked about identity. I began my sabbatical deciding I was going to become a computer scientist. And then I hung out with computer scientists, and I think I became a computational neuroscientist again. And I think the important thing is realizing what your fundamental questions are, and mine have always been about trying to understand the computational mechanisms that give rise to social behavior. So in this sense, the collaboration is really just a whole new set of tools that's allowing me to do the things I've always wanted to do. It just happens to be in a different department.
All right, let's thank our speakers again for this very inspiring talk.